Howdy again, everybody. So we're going to continue on with the sort of high altitude view of what we're going to cover in this course. So all that we talked about previously, those electrostatics pieces, charge properties kinds of things, are sort of the foundation for everything that we're going to be working through in Phys 2. And at the end of that, now that we've established some of those basics, fundamentals, where things come from, especially capacitance, capacitors are going to be that nice segue for us to say, well, how do we actually charge these things? How do we discharge these things? How do we wire them together? What are their uses? And that study is going to really lead us into circuits. And so some of the basics that we're going to talk about with circuits is just how do we draw circuits? What do they represent? And those sorts of pieces. So the capacitor, because we tend to think of them as these parallel plates, where in reality they're often these big sheets that we build, oftentimes with something sandwiched between them to prevent the sheets from touching, and to serve as another purpose that I'll talk about in a little bit called dielectrics. And of course, as with everything else, we'll really delve into huge detail later on with all of these pieces. So there'd be like this dielectric sandwich of a different material in here. And then we would kind of take this whole thing and roll them up. So oftentimes capacitors look kind of like these little cylinders because we took these little like cinnamon roll spiral things and rolled them up. But because the simplest one to work with, and at some level, they're always two sheets of metal separated, we use this as the symbol. And so then I would have this capacitor here, often labeled like C1 or C with some number, and we would wire it up to, maybe I could wire it up to, let's say a battery will be the first component that I wire it up to. And so this being the battery symbol, each cell of a battery looking like this, with the positive end being the longer one, the negative end being the shorter one. It's a pretty common convention that we'll see across a lot of different components in circuits, is that if there's ever a reason for there to be a quote unquote positive or quote unquote negative end, we'd have to have those paired together. There's typically like the short end of the circuit component. So if I had, based on the manufacturing here, the longer lead is going to be the positive end, and the shorter lead would be the negative end. And because you could just, take some scissors and cut that, you're like, oh, we don't want that. There's also often some other secondary indicator, like this big tape with a big minus sign on the minus side of things. Similarly with diodes, they've got some junk going in here with this kind of looking thing and this other looking kind of thing. And because of quantum mechanics that we won't really talk about, there's sort of this indicated polarity that has this preferred direction of current. And so to indicate that, they'll typically say this end is the negative end, and this end's the positive end. And these ones don't often have that unless you know how to look into here. In some LEDs you can, some LEDs you can't. Depends on the opacity and all sorts of other bits and pieces. But that's just a typical convention that you see. And these batteries then, with the positive and a negative end, notice I put two of those right in sequence. That indicates that it's probably at a higher voltage. This is probably a 3-volt battery, because typically one cell of a battery is 1.5-ish volts. That's what you see across all of your batteries. So if you've got like your AA battery, or you've got like a AAA battery, which is the same voltage, but it's just smaller, or a quadruple A battery, which is the same voltage, but even smaller. And those are even the same voltage as if you have like these C or even bigger D batteries. They're all made out of these 1.5 volt cells. And a lot of times, even 9-volt batteries, they're just a bunch of those 1.5 volt cells, but they're wired with like 1, 2, 3, 4, 5, 6 of them in a series. And that series has this property of voltage being additive. We'll see that embedded throughout all of this kinds of circuit stuff. This idea that voltage is added in series comes up a lot. It's one of the fundamental things that comes from essentially conservation of energy, in the same way that conservation of charge is going to come from saying, if there's only one path, the current through this whole loop has to be exactly the same thing. Current being this word that we use for the flow of charge. And so what we end up seeing is that if I just plug in, this is the positive side of the battery, this is the negative side, very quickly, almost instantly, if there's no what we call resistance in the circuit, this capacitor gets fully charged proportional to, well, if we know this capacitance and it equals Q over V, and we know the voltage of the battery, you can just multiply this over to find the charge that this capacitor reaches. And then very quickly, we're going to want to look at other properties of these capacitors as well. Things like, well, that's how much charge the capacitor stored, but what about the energy stored in the capacitor? And we'll walk through a longer derivation of where this comes from, where the energy stored in a capacitor is 1/2 times the charge times the voltage. We talked a little bit about where this 1/2 came from earlier, but it'll be more thoroughly satisfying when we do it a little bit later. And the other bit is with this Q times V. We saw that for point charges, it was the case that the potential energy stored between 2 point charges was just equal to Q times the V. This is used as a derivation for this, but this only works for one pair of point charges versus a capacitor is just like a bajillion different little positive charges kind of held near each other. And they're held near these negative charges on the other plate. And this is a large and complicated distribution of charges. That's where eventually it boils down to this sort of formula, where this Q is the sign of the charge plus Q on one plate minus Q on the other plate of the charge stored in this system. And the voltage is the voltage that these are held between, which in equilibrium, we're going to learn this back even in Unit 1. I didn't really talk about this, but one of those properties of conductors and how we know that the charges redistribute is they seek an equilibrium. And one of those equilibrium conditions is that this conductor is at a constant voltage and this conductor is at a constant voltage. And because voltage is a scalar, that means if I go from any spot here to any other spot here, doesn't matter what path I take. If I take this path or this path or this path, any of those paths are going to have the exact same difference in voltage, therefore guaranteeing this voltage drop, voltage difference, potential drop, all of those words we start using when we're talking about circuit components. And for instance, if I color up here, this entire wire up here is going to be all at one particular voltage. And then down here, this wire is going to be all at one particular voltage as well. And so anywhere you go from red to blue, that's high to low, you have that same voltage drop. But that also means if you go around in a circuit, you start here, gain voltage, no change in voltage, lose voltage, no change in voltage. When you return to the same spot, you always end up with a net voltage change of 0, which is a statement of conservation of energy. It's something that we call Kirchhoff's loop rule. And it's something that's sort of implicitly embedded inside of everything we do in circuits, whether it's capacitors and batteries, or the next component that we'll talk about are resistors, which you could do the same sort of thing, where you have a battery in series with this thing we call a resistor. And I'll try my best to draw one. It's like these sharp little spikies. And because that's annoying to draw, and because this will look similar to a third component we'll talk about later, an inductor, which for some reason we use the letter L to represent, which has units of henries. Again, we'll talk about that later. A resistor, which has units of ohms, a Greek capital O, a Greek capital big O. There's lowercase o, micron, and omega, because you've got that little W looking thing as the lowercase and this horseshoe thing. And then omicrons look like our O's. Omicron, notice that small omega, big O. So there's lowercase and capital case, big O and small o. Look, the Greek language is a very strange thing. I was not consulted in the design phase. I'm just here to tell you how it works. So this is what we call an ohm for the unit of resistance. And basically what it's saying is that if I connect these together with just a wire, current wants to flow. Current we'll use the letter I for. Again, not really a good reason. I has units of amps or amperes, short for ampere. This current flowing here from positive to negative, it wants to flow, but if there's essentially no resistance, it would flow super quickly. We would release a lot of that energy that's stored in this battery, that chemical potential energy, and it has to go somewhere. And typically what that means is it turns into heat. A resistor is sort of the thing that impedes this flow. So when we put in this resistor here of resistance R and this voltage V, we get a current that we measure according to the equation of V equals IR, or if I just divide this over, I don't know why my pen stopped working. It's doing strange things. Hold, please. There we go. This is how we would get the current. And this is sort of an experimental factor. We'll do some labs around this where we get and build some intuition. We'll do some simulations with this. This is, again, sort of that high altitude info dump, exposure to lots of equations that we'll end up seeing. And just like with capacitors, where we're also interested in talking about the energy, we'll talk about energy with resistors, but resistors have to deal with the flow of energy, not the store of energy. So the rate that energy is spent, the power. And so power across any circuit element is P equals IV, the current through that element, times the voltage drop across that element. And so if you do some substitution with Ohm's law over here, that we call this, again, somebody's last name, that's where we can start to get some substitutions of like either I squared times R or V squared over R, notably not centripetal acceleration being that tangential speed squared divided by the radius of curvature, sometimes used a lowercase r. It's not that same thing, though there will be problems, sometimes the same problem, where you'll have both this V squared over R and that other V squared over R if there's some circular motion of charged particles moving as well. And similar to this, how there's different forms of this will work for everything, but resistors specifically get these extra forms. In that similar way, if we bounce back to our capacitor equation, where we had this potential energy stored in a capacitor of 1/2 QV, because capacitance also equals Q over V, this means that you can say, I'll try to switch to my other pen too, that I have better handwriting with. Because C equals Q over V, I can make any substitution here. So if I, for instance, solve for V here, I can replace this voltage with Q over C, and we get these alternate forms of it. So it could be either 1/2 QV, but it also could be better written, or depending on the problem, as 1/2 CV squared, or as 1/2 Q squared divided by C. So we have those alternate forms from those algebraic substitutions for some of these pieces. So those are some of the basic circuits things that we'll talk about. The other thing with each of those is there's going to be rules for combining these objects together to make our lives more simple, because yes, we could use just these ideas of conservation of energy, that Kirchhoff's loop rule, that every time we go around a loop, you end up with the same voltage, no voltage difference, that is. So if I had a more complicated circuit, like a battery going into one resistor and then another resistor, I could call this R1 and R2 and say, okay, I'm going to gain voltage, then I'm going to lose voltage, and I'm going to lose voltage, and get one equation. And then also say that because it's one loop, I have to have the exact same current everywhere and do some substitutions. You could do that and set up this ever-growing set of linear equations. Like if I added in this other piece over here with a third resistor, I'd have to have a separate piece where this voltage drop here is actually the same as these two, because they reach that same point down here. Again, we'll always talk more about this in much more detail. We will have equivalent adding rules for how to find these pieces, where when we have the resistors in series, it's really easy. The equivalent resistance is just add up each resistor. So if I just did like R1 plus R2 here, that'd be the equivalent resistance of this branch. And then I could effectively replace that whole branch for temporary analysis with an equivalent between 1 and 2. And because of that equivalency, I can now use Ohm's law to figure out the current here, and then zoom back out. Now that I know the current, I can now find the individual voltage drops through each of these because the current is the same through those. So if you just add up each resistance in a series, you get the equivalent resistance of that theory. But if those resistors are in parallel, like this equivalent resistor and this R3R, because you reach here and there's a fork in the road, I could either go down this path or I could go down this path. So the total resistance of this path plus the total resistance of this path if you wanted to find that, it's a much more complicated rule that we will derive and we'll figure out why later. But it really comes down to this idea of 1 over the equivalent for parallel is you add up all of the 1 over each resistor. And then if I wanted to solve for this, I would then do 1 over all of this. So what that would end up looking like is I would do 1 over R1 plus 1 over R2 and do that for as many as there are. And then at the end of that, if I wanted to solve for that equivalent, so in this case, I'll call it the equivalent being 1 over the equivalent resistance of 1 and 2 plus the equivalent resistance of 1 over R3. And then I have to take all of that and 1 over that, which oftentimes to save space, we'll do like to the -1 to indicate the reciprocal. That's sort of the flavor of how we'll do those pieces. And there's similar adding rules for the capacitors, but they're flip-flopped for reasons that we'll talk about. The equivalent resistance in series for capacitors is going to do this weird like 1 over thing, however many of those terms we have, which often we compactify again by writing it like C sub I with our sigma notation here. And for parallel, it's that easier rule for capacitors where you just add up C1 plus C2 plus da, 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 da. And so really it's you add up each capacitance. And then it gives you those equivalent pieces. And then from there, you can apply instances of C equals Q over V and rules like, oh, in series, the charge is the same. And in series, the voltage adds, or in parallel, the voltage is the same. And the charges add. We'll work through all of those kinds of pieces later. This is sort of just that high altitude view of the things that we'll come across. And we'll revisit all of these pieces later. This is the idea. I always think of it like gardening. You're planting lots of seeds, and then we'll come back and we'll water them. We'll pay each one closer attention, and we'll have them grow. But it takes setting out this broad foundation, letting some of those pieces sink in. Then we revisit them later. So we've talked about a lot of those pieces. So we talked about resistors on their own, capacitors on their own, and or in the context of with batteries. The next thing that we end up doing is we start combining these pieces. We say, well, let's say if I have a capacitor that's connected to a resistor, and maybe I have a switch here, and I start off with this capacitor all charged, and then I close this switch. What we end up finding happens from those Kirchhoff's rules that let us build a differential equation that will solve. Yes, I know that Calc 2 has not yet been done for some of us, and there's a differential equation using that, and then there's a bigger differential equations class altogether. Don't worry, we will take each piece slowly, we'll work at them one at a time, and really we will be fine even if we aren't in Calc 3 or DiffyQ or in neither. We will be okay if only in Calc 2 as the co-requisite requires, but it might be a little bit of extra math and struggle for that. But then keep in mind, that means that when you get to those classes later, you should be at a stronger foundation. So the idea here is if I have this capacitor and I'm discharging through this resistor, the voltage across this capacitor starts high, but eventually it gets to 0. And it does this, as we'll find when we solve that differential equation, in this exponential decay. This is, again, if we're graphing that capacitor voltage as a function of time. And it turns out that essentially every quantity has these relationships that look like some sort of exponential decay with some sort of asymptote, some sort of initial condition, and some sort of asymptote. But they're not all the same. For instance, if I wanted to graph the, let's draw a different circuit, because for this circuit, they actually would all be exponential decay. But for a charging circuit, so a charging circuit would look like if I have a capacitor in series with a resistor, and I have a battery that I'm going to use to charge this circuit, and then I have a switch, and I then close that switch. What we're going to find is that the voltage on this capacitor starts at 0, but eventually goes to some asymptote, some fully charged state. And it turns out that if the resistance is just really low, it gets faster and faster to the point where it basically looks instantaneous. It looks like this step function where there was no voltage, and then one just fraction of a second later, it becomes that fully charged state. What it's really following is this sort of exponential curve. So these ones always look like an e to the negative t over some sort of characteristic time that we call tau, lowercase Greek t, tau. And that's what we call the time constant. For reasons we'll find out later, it's related to the resistance times the capacitance. So a bigger resistor and or a bigger capacitance would make this process take longer. And then this is just a transcendental function, right? Time over time, no units. And we can build this out of a whole sum of other functions that all have no units. That means the way that we get units is by adding in essentially the initial voltage here, the characteristic voltage of that system. Or in here, the boundary condition is the final case. So the final voltage times, and the way that this transcendental function looks like, there's a part of it that looks like e to the negative t over tau. But it's this 1 minus structure that gives it this flip and then vertical shift to make the initial condition 0. And then we multiply by that final boundary condition according to this. Some of this we'll get into solving differential equations. Some of it will get into mathematical modeling kinds of ideas. And again, this is sort of just a shotgun blast of all of the information that we'll really, really delve into in much more detail as we more slowly take on all of these pieces. Some of the last bits that we'll do in circuits before we get into typically the end of Unit 2 and our exam 2 is dealing with alternating current. Everything we've done up to this point, you close a system, you let it go, and it just evolves as it happens, and it reaches a steady state that is everything flowing in one direction, or the flow decaying, or reaching some sort of steady state. In alternating current, the big difference is instead of the voltage source, so if I just graph the voltage as a function of time that a battery provides, it's steady, it's constant. Sometimes it's 0 if there's no battery involved, if it's just wires hooked up to each other. Sometimes it's a constant non-zero. Sometimes it's like a negative constant to indicate polarity, what direction we send things in. But the fundamental difference between DC, what we just talked about, and AC, alternating current, is that the voltage as a function of time is essentially a sine or cosine wave. It wibble wobbles back and forth. And this is typically what happens 60 times, 60 hertz, 60 times per second in the lights that are probably on above you right now, at least in the United States. There's other places that will do 50 hertz or like 100 hertz. A lot of it has to do with SI, electric grid kind of things. But then the amplitude here is the other piece that's going to indicate intensity. And everybody's probably like, oh, it's 120 volts. Not quite. The peak is actually closer to like 170 volts. And what that 120 volts is this rating called a RMS voltage, a root mean square. And so what that means is we're taking the square root of the mean of the average, the time average, of the square of whatever that voltage function is. And what we find is that when you do this, the peak voltage times root 2 over 2 is always going to equal this so-called RMS voltage. So this 120 volts RMS, this is where if you divide that 120 volts by root 2 over 2, you're going to get that, that 170 volt peak. That really is what we're dealing with in our electric grid. And we might ask, well, why would we invent this thing? Why would we add this extra big pile of nonsense? We wouldn't do it for no reason. The reason is when we look at things like, for instance, power equaling current times voltage, if I take the voltage that looks like this, and I multiply it by the current that, well, because V equals IR through light bulbs, well, the average voltage is 0. If I just wibble back and forth, it's positive for some time, and then it's negative for some time, it's positive for some time, negative for some time. If you take the average of this function, it's 0 over any period. And that would also be true of the current. So if you're trying to get like an average power by taking average current times average voltage, it wouldn't get you anything because 0 times 0 equals 0 squared, which is 0. It's super nothing. But we know that I have to pay for energy. I don't just get energy for free. So we invented this idea because when you take this whole function, and if V equals IR, that means the current function also kind of looks the same way. So when the current is flowing one way, the voltage is also pushing it essentially the same way. And when you take those functions and multiply them together, the power function actually looks always positive. You're always spending energy because a negative times a negative equals a positive. And the average of that function is not zero. And so what we do is we invented this math because at some level, when you take a function times a function, at some level, that's where if you look at the other function of either v squared over r or at your at either v squared over r or at I squared times r, you're taking that function squared. And that's where when you take this average to like renormalize it, you square root it, but you take the square thing to go from any individual piece to the power. That's sort of the utility of this so-called RMS value. And that will also have relationships to some of the other pieces that we'll talk about with some of the math. For instance, if I have this alternating source of current, instead of it being a battery or just a voltage source, or sometimes they'll just do a plus minus. Sometimes it'll be like a plus minus, but with this little twiddle sign to indicate that it's an alternating current. And if I put that alternating current into a capacitor and or resistor, we're going to see some really interesting behaviors where this voltage source, this V as a function of time, is actually going to act with this capacitor being more like a resistor than a capacitor for alternating current. Because, let's delete that resistor for a second. Essentially, if I push on positives here, it gets negatives over here on the other side. And it gets harder and harder to push on positives the more I have to push them onto the same side, to the point where it would have effectively infinite resistance in that DC limit. Eventually, that's what we saw, is that it reached this steady state where it had achieved a certain amount of voltage and a certain amount of charge. But what we're going to find here is that those lower DC states have a higher quote unquote resistance, because eventually this will swing backwards and these positives need to go back over here and sort of switch sides so that all of these become negative and all of these become positive. But then it has to switch back again and switch back again. And the faster you do that switching, the less total time it has to build up charge. So it's just one on, one off, and then it switch sides, and then take it off, and then put it over here. And it doesn't take a lot of resistance. It doesn't really impede that flow very much. So what we find is that capacitors and alternating current look kind of like resistors, but they have this frequency dependent resistance versus resistors. They always have the same resistance. Resistors always follow this V equals IR rule, versus a capacitor, which is going to follow something that looks like V equals I times this like X factor, which we're going to call reactance. But the reactance of a capacitor is going to be equal to 1 over 2 pi times the frequency times the capacitance. Technically, there's an imaginary number here. We'll not worry about that. Actually, even super technically, it's like a 1 over negative. We'll talk about that later, maybe a little bit in detail. But at some level, what we do to find a net resistance, a so-called impedance, that was kind of why I injected that word earlier. We call this total impedance Z. For reasons we'll find, it looks like Pythagorean theorem, where we take the reactance squared, add it with the resistance squared, and then square root it. So resistance, reactance. And we find this sort of trend all the time, this semantic trend, this trend with words in E&M, where we put in a bunch of like synonyms close together, where resistance and reactance and impedance, they're all very similar synonyms. And that's intentionally chosen, where they're different enough that we can distinguish between them, but they do have distinct meanings and they intermix in this very particular way. Again, we'll explore those mathematical relationships in much more detail as the course goes. This is sort of just that high level view of then what we'll be able to do with some of these tools is build out some filters. So if I have a resistor that goes into a capacitor, or sometimes we'll switch the order, we'll be able to attach some probes here and either have like a low pass or high pass filter, as we call them, because they're able to pass on voltages at high frequencies or at low frequencies. And so, for instance, a high pass filter is going to filter out all of the low frequencies that maybe we don't like. Maybe my voice is driving us crazy because it's this super deep low groan, and we want to make it a little bit more palatable. That's where we might put in a high pass filter to filter out some of those lower frequency pieces. Or we could do the opposite. If you're like, oh, this dog whistle is driving me crazy, we could use a low pass filter to filter out some of those higher frequencies. And at some level, we have to do that in an analog kind of fashion, or digitally now with some transistors and sets of pieces. But back in the day, we would do this really electromechanically with some of these resistors components. And some audio engineers that are really dedicated to the trade will still do some of these audio processing in analog with vacuum tubes and or with other kinds of pieces. So we'll talk about uh, some of those pieces when we get there. And that's typically where we would break for exam 2 to check our understanding and make sure we're refining and building all of our knowledge with these things, just like we've done previously for our electrostatics pieces. And then we would jump into magnetism, where eventually we'll even discover, I hinted at earlier, that new circuit component, this inductor, and related things where we put two of them next to each other, sometimes with an iron core, called a transformer. Not a robot in disguise, but these are how we do power modulation, how we generate power and then step up the voltage to send it somewhere else. And we'll get to talk about a lot of those kinds of cool pieces, but it's all grounded in these magnetic and electromagnetic theory kinds of pieces that I'll talk a little bit about at that high altitude view in the next video, and we'll delve into in much more detail probably a couple months after we hear this first little info burst. So I'll end this video here. Thanks for joining me, and I hope to chat with you in the next one.